Hello, everyone. I seem to only have three people in the watching the stream right now. Can any one of you just tell me if you can hear me? I'm seeing the levels are good right now, but confirmation that you can hear me is always good. And also, I'm going to wait just a few more minutes to make sure that just a few more seconds to make sure that people pop in. I see someone else has just popped in. So. Um, well, let me start giving some of the background before I actually jump in and do problems. So you should have watched this week the video on all the videos on 2D kinematics and the video on 2D kinematics constant acceleration and 2D kinematics uniform circular motion. And that'll be it for the topics up to the test. Next week, I'm not going to be, we're not going to be watching any more new material. I'm just going to be doing live streams all week long and going over problems like the problems that you'll have on the test. So you will have another assignment next week at the same time that you're, studying for the test. But that's okay because the assignment will be on 2D kinematics, which will be on the test. And I recommend that you do it early so that you can use it as a studying tool and ask me questions if you're early on before the actual test. Okay, I'm also going to give you a couple of practice questions at the end of this lecture, so that you have a lot of problems that, in addition to the assignment, a lot of problems to work on in 2D kinematics. So the 2D kinematics, I think you're starting to see, is a little bit more demanding than 1D. There's quite a few steps, and so the purpose of doing this is I'm going to go over a lot of the stuff that you saw in the pre-recorded lecture, but I'm going to be doing it, interactively with you, and I encourage you to ask questions or tell me if I'm going too fast, because I usually cut and paste, and the reason I do that is so that I don't make typos as I go along and so on, but not to go too fast, okay? Because I assume that you guys are taking notes while I'm doing this, okay? And with the pre-recorded the problems of the pre-recorded lectures and watching me doing these things interactively with you, hopefully you'll get enough information to be able to do these problems on your own. Okay, and so let me see here. We got 5 concurrent. Yeah, great. Thanks, guys. I can see that you can hear me. So, well, let's start off with the problems then. Well, maybe I should show you what we're going to do. So I've got that one problem that we're going to do together, and then parts 2 and 3, or problems 2 and 3, I'm going to ask you guys to do it. They're variations on the first problem. The first problem, I'm actually at the bottom of the hill and I throw a rock and it lands on top. It's actually the problem that I didn't do during the pre-recorded lectures. I kind of mentioned it at the end as a possibility. We're actually going to do it right now. And then problem 2 is a variation on this, only you're both throwing the ball and it's landing at ground level. And then variation number 3, which you'll do on your own here, problem number 3, is you're standing at the top of a hill and you're throwing it down. Okay, and then we'll also do a problem on uniform circular motion. But to be quite honest, uniform circular motion is really straightforward. Okay, so there's not much that I need to do. It's much better that I spend time on the 2D constant acceleration to make sure that you know how to do those problems. Okay, so let's start then. The first question is, oh, can't see it all. Let me just do that and do that. Okay, now you can see it. Okay, so I'm standing at the ground level. Okay, and I toss a ball with a velocity of 25 meters per second. That's not too fast, but you can easily toss a ball at that speed at an angle of 60 degrees above the horizon. And what the 60 degrees above the horizon means, I'm going to show you that when I draw the diagram. Okay, so the ball goes up. I'm at ground level. The ball goes up, comes down, and on the way down, it lands on the top of a hill, which is 20 meters high. Okay, so 5 questions. Question number 1 is how long until the ball reaches maximum height? And question number B is what is maximum height? Let's do A and B together first, okay, because they both have to do with maximum height. C, D, and E have to do with the ball coming down and then landing at the top of the hill, okay? So what do you do with this? Now, my tests are like my assignment, okay? They're multiple choice questions. So when you get to the test, you won't be surprised by anything. They'll look a lot like the questions in the assignments. This is one of the reasons to do the assignments. But you're still, just because they're multiple choice doesn't mean you're not going to have to have pencil and paper ready and you're going to draw things out. Okay. Most of the mistakes that are made in these solving these problems has to do with not drawing the diagram correctly, not getting the right numbers off of them, not plugging in right. So in 1D we saw that, but in 2D it gets all the worse or all the harder because there's initial and final position, initial final velocity, acceleration, and time. But the initial position, that's two numbers because now we're in 2D. Final position, that's two numbers. Okay, so there's more work and we got to be a little bit more careful. And then also there's the business of converting between polar and Cartesian. Okay, so let's start off. So the first step is to draw the diagram and draw just what you would see physically. So here you're standing at ground level. There's a hill 20 meters, 20 meters high, and you throw the ball, it goes up and it comes down. All right, so let me switch to my other whiteboard here like that. Okay, and I'm going to draw this in black. So just what would you physically see? Well, here you are at ground level like that. Here's the hill, and then the hill is 25 meters high. I'm not going to draw the 25 meters right now. It's just like, what can I see? Okay. And I'm here at ground level, and I'm not even going to try to draw myself. Okay. I'm just that dot. That's me. Okay. And I throw the ball up, and I'm going to draw the trajectory. I'm throwing it at 60 degrees. So this would be about 30 degrees. That would be about 45. 60 degrees is like roughly like that. It goes up, 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 reaches maximum height, comes down, 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 down like that, and it lands at the top of the hill like that. Okay, so there it is. That's what you would physically see. That's the first step in what you would draw. Okay, the next step is you have to add a coordinate system. Whenever in physics we say the word coordinate system, it means both a ruler, that is a measurement of distances, and also time. Okay, now time you can't really draw, okay, but at least you could say where t equals 0, so where is this ball at t equals 0. Okay, so let's do that next, and I'll do this in blue. All right, so we got to do the rulers. This is 2D, and in 2D you have two directions that you have to measure, two dimensions. Okay, there's the x, and that we're going to always do horizontally. Okay, now the reason we're going to insist on always doing x horizontally is the equations that I'm going to give you later. I'm going to give you 4 of them. Those equations that I'm going to give you later, they only work if you choose x horizontally and y vertically. You don't have to, but then you got to redo the equations, and it's just not worth it at all. Okay, so this direction here, that's the plus x direction like that, and that is horizontal. Okay, now and you'll see this in the assignment. I don't just give you this and ask one question about it. I give you a bunch of questions, and I break them up into pieces. So like one of the questions might be what is the initial position, and to answer that uniquely, so that we, because this is multiple choice, you have to match your answers to what my answers are. Okay, to do that, I got to tell you where the origin is. In reality, you could choose the origin anywhere you like. Okay, but I would on the test or on the assignment that you'll see next week, I'm going to tell you where the origin is. Okay, and you can choose it anywhere, but I think it's pretty obvious that you should choose the origin on me. That is where I throw the ball. Okay, and that's where the x and y axis meet. All right, so here's the y axis like that. Oh, I missed it a little bit, but close enough. All right, there it is. So there's plus y like that, and where the two meet here like that, and here I'm just gonna make my dot a little bit bigger like that. There we go. Okay, where the two meet, that's the origin. I just put a 0 there like that. Okay, really it's 2 zeros. There's a 0 in the x and a 0 in the y, but 1 0 is enough, and that basically says that is the origin in the plane. Okay, and the reason you need both x and y is like I'll take this dot out in a minute, but take a look at that red dot there. If I said where is that red dot, you can't answer that without telling me two numbers. You got to tell me like how far horizontally do I have to move? Okay, how far horizontally here do I have to move to get to that x, to the underneath that? Okay, that's your x value. And then how far do I have to move vertically to get to it? If I just give you one of those two numbers, say I give you only the vertical, well then you know how high it is, but you don't know where it is horizontally. Or vice versa, I give you x, then you know how far you go horizontally, but you don't know how far you go vertically. So you need both of those numbers. Okay, and that's why you need an XY plane. All right, great. So there's the X ruler and the Y ruler, but like I said, you also need time, and we're going to say where is t equals 0? That's like if you had a stopwatch, and where are you going to press the stopwatch? At which point in the motion you're going to press the stopwatch 0? You can actually press it anywhere you like, but I think it makes a lot of sense to choose this point right here. That is when I let go, that's t equals 0. Okay. So there you go. So there's the coordinate system. It's the XY plane and also the time. Okay, the time origin. So the time origin again is when am I going to press the stopwatch to start taking away the time, and it's as soon as I release the ball right there like that. Okay, so there's step number 2. Let me see if there's any questions in the chat. All right, no questions. I mean, it's pretty straightforward up till now. I mean, these are exactly the same steps that we did in 1D, but now we're in 2D. All right, and then the next thing is we have to get to the initial position, final position, initial velocity, final velocity, acceleration, and so on. For questions A and B, I mean, you can't see them there, but let me just reread them to you. How long until it reaches maximum height? Okay, how long until it reaches maximum height? And maximum height, I know the ball is going to eventually land on the top of the hill here, but right now we're only worried about the motion from when I release it until it gets to right there. So when I say final, I mean, that's probably not the best name for it, but that's like what all physics textbooks call it. Final just means after the time t, when it gets to the point that we're interested in. And the point that we're interested in is that red dot, because that red dot represents maximum height. Okay, so the initial is down here. That's your t equals 0. And your final, that's like when you get to the point that you're interested in, it's up there. And by the way, we don't know how long it takes to get up there. And that, in fact, that's your first question. Okay, so we don't know that time. And so now we're going to go through all of the quantities. I can't fit them all here, so I'm going to have to switch back to the other whiteboard in a minute. But let's do the initial position. So in the initial position, it's 2 numbers. It's both x naught and y naught like that. Okay, so I'll even put a little bracket there like that. So when I say initial position, I really mean 2 numbers. And you'll see that one of the questions on the assignment and also on the test, I'll give you a situation like this, and I'll say, what's the initial position? And you'll see that all my answers will have x naught is equal to, y naught is equal to, okay? Because you need both, all right? And so where is it initially at t equals 0? Well, it's obviously at the origin, and the origin is x naught is equal to 0 meters, and y naught is equal to 0 meters. Okay, so great. There's your initial position. That's 2 of the numbers that you're going to need when we start substituting into those equations. Okay, so we'll go in order. Initial position. The next one is final position. Final position. Position again is 2 numbers, and these are Cartesian, x and y. Okay, so final position like that. All right. So x is equal to what, and y is equal to what? All right, well, let's see if we can read them off of there. Well, let me get rid of the question mark. The x, it is a question mark, but let me show you why. I mean, x is like how far did you move over horizontally. So if I just draw the projection here, and the projection is, you could imagine like the sun is up above, and this is that dashed line is like the shadow of the ball being projected on the ground. And you would just look along the x ruler here and go, okay, what am I reading on the x ruler for the distance that of the shadow from the origin? And you don't know. Okay, like there's you can calculate it, and we will, but you don't know because nowhere did I ask you that. Okay, sorry, nowhere did I give you that. Okay, and so yeah, we don't know that, and so that's a question mark. Okay, so let me get rid of that dashed line just because I don't want to make a mess of this diagram. Okay, question mark like that. Okay, and the next one is, what is y? Okay, so what's y up here? Y, in these problems, wherever you see the word y, or wherever the variable y, that's basically your height. Okay, that's your height. And again, if you read the problem, you don't know. In fact, that's what we're trying to solve for. So that's not only a question mark, but that's what we're trying to solve for right there. Okay, and so let me get rid of that dashed line. Oh, I should draw that question mark afterwards. Okay, so that is question mark like that. Okay, so initial position, final position, and now let's do initial velocity and final velocity. Okay, so we just did that lecture, well, this week on or sorry, last week on vectors. Okay, and I did all this business about converting between Cartesian and polar, polar and Cartesian, and you go, well, why did you do that? In doing these, we need Cartesian values. Okay, the equations are all in terms of Cartesian values, and so we have to work in terms of Cartesian values. And so when I say initial velocity, I'll do it up here because I don't have enough room down there. Initial velocity is 2 numbers again. It's v naught x and v naught y. The naught means initial, and the x and y are the components like that. Okay, but if you read the problem, and I'll reread it for you right now, I say I toss a ball with a velocity of 25 meters per second at an angle of 60 degrees above the horizon. So a velocity of 25 meters per second and 60 degrees. That's polar information. But that's not what you want. You want the Cartesian information. And so you have to convert from the Cartesian, sorry, from the polar to the Cartesian. Let me draw for you. Maybe yellow might work here. Let me draw for you um, what this 25 and 60 really mean. The velocity, the direction of the velocity is along this yellow line here like that, okay? Okay, and that's 20, oh, that might be a little too light. I don't know, let me see here. At my end, I can sort of see it. Okay, so yeah, I mean, I can see the yellow vector, but the 25 is a little bit light, but I can see it. And just holler at me in the chat if you can't see it. But there's the 25. That 25 is called the magnitude. It's just like how fast is this thing going? 25 meters per second. How fast is this ball going? I don't care the direction, just how fast is it going in whatever direction. Okay, and that's called the magnitude. So when we did the polar Cartesian stuff, that was like r. There, you might think r is like the radius, and it is if you're just talking about a position. It's like the just the distance, irrespective of direction. But if you're talking about velocities, that r in the conversion formulas can be any magnitude. It could be just like the magnitude of the velocity, in which case it's just how fast is it going irrespective of the direction. Okay, so there's the magnitude, and you also need the direction, and I tell you that the direction is 60 degrees above the horizon. So the horizon, if you were standing here like at ground level and you look to the horizon, that would be looking directly along the x-axis like that. Okay, and that, if you turn to the angle at which I throw it, I said that that's 60 degrees. That is your theta like that. Okay, so you have that your magnitude is 25 meters per second and your angle to the x-axis is 60 degrees, and that's what you use to substitute into the formulas here. And the formula, it would be v naught x is v naught cosine theta, and v naught y is v naught sine theta. Okay, and I'll substitute in when I switch back to my other to my text editor. But basically, that's how you go from the information that I gave you in the word problem, that is the velocity and direction, okay, the magnitude and the direction. You go from that to your x and y components. And you go, well, what does this x and y component even mean? Like, could I draw that on the diagram? I can. I don't want to make this too messy, but let me try to draw this in green. If I were to take this vector here and break it up into its x component, it would be like the x component of the velocity would be like how fast is it moving to the right, okay, and the y component would be how fast is it moving upwards initially, like that. Okay, so v naught x is the horizontal green arrow and v naught y is the vertical green arrow. And if you need to picture that, the way I like to think about this is imagine that the sun is directly overhead. That doesn't happen in this part of the world, but like there are parts of the world where during some point during the year the sun is like literally directly overhead, okay, like at the equator. And of course there would be a shadow. All right, and so like take a look at that red dot I drew up at the top here like that. The shadow, I drew it earlier. The shadow would be directly below it, okay, like that. Okay, now the ball is going up and it's coming down, so it's moving up and down like that. But if you were to watch the shadow on the ground would move to the right at actually a constant velocity, which I'll show you in a second, but it'll be moving to the right, and that's what that green arrow, the horizontal green arrow, means. It means the velocity of the x component, and that is the velocity of that shadow that would be projected down to the ground. Okay, so that's the x part. The y part, of course, it goes both up and down. So initially, it's moving in an upwards direction, so it has an upwards component. It gets to the maximum top. It stops at the top, so the Vy becomes 0 at the top, and then it starts to come down, and then the green arrow would be in the downwards direction. Okay, so that's what's happening with the velocity. That's the meaning of V naught x and V naught y. Okay, so let me switch now to the other editor here, or my text editor like this. And the first question is how long until it reaches maximum height. So not to go too fast, so give you time to write this down. I'm standing at ground level and I toss a ball with a velocity of 25 meters per second at 60 degrees above the horizon. How long until it takes, it lands on top of a hill 20 meters high. How long until it reaches maximum height? So we're not even worried about the hill for question A, okay? At this point, we have that diagram completed, and here I'm just going to cut and paste, but go over it slowly with you. All right. We look at the diagram, and here are the values that we have from, whoops, I put it in the wrong place. Here we have for the values that we got. So for the initial position, we found that x naught and y naught were both 0. It starts off at the origin, okay? The final position, we also looked at that. We didn't know how far it moved horizontally, so x is question mark. We didn't know how far it moves up to its final position vertically, and so question mark there too. In fact, maximum height, y, that's one of the things we want to solve for, okay? Not in part A, but in part B, okay? Part B, just to remind you, is what's the maximum height achieved, okay? So it's one of the two things that we want to solve for. All right, and then we had the initial velocity, and the initial velocity had an x and y component, so there's v naught x and v naught y, and v naught x is v naught cosine theta, like that. Substitute in the numbers, which is 25 cosine theta, like that, and if you crunch that through your calculator, you will get 12.5 meters per second, all right? So cosine 60 is probably one of those angles that you should memorize. The cosine you should memorize. Cosine of 60 degrees is a half. Cosine of 30 degrees is sine of 30 degrees is a half, and cosine of 60 degrees is a half. Okay, so half of 25 is 12.5. All right, and then you do the same thing for the y, but the y is the sine component, and so you got v naught y is v naught sine theta, 25 sine of 60 degrees, and that turns out to be 21.7. Okay, so the two components have to be less than 25, and it works out. Okay, so you know the x component is 12.5, which is less than 25, and the other one is 21.7, which is less than 25. Okay, because you've taken the 25 and you've broken it into two pieces, x and y, so the two pieces are less than the total. All right, there you go. Okay, and then there is the final velocity, and that's the final velocity when we get to the top. And Vx, I said that Vx is equal to V naught x. Now that one you might go, why is that? And I did mention it in the pre-recorded video, but what's going on here is because we put the x-axis horizontally, there's no acceleration left to the left or the right. The acceleration is straight down, okay? I mean, it'd be weird. We'd be living on a funny planet if I let go of the ball and it, accelerates down but also to the right. Or, I let go and it accelerates down but also to the left, okay? But it doesn't accelerate to the left or to the right at all. It just accelerates straight down. So ax, which would be the acceleration to the left or right, is 0, okay? And so if there's no acceleration to the left or right, that means that the velocity isn't changing horizontally. And that means that if you start off with an initial velocity v naught x of 12 meters per second, okay, if you start off with an initial velocity of 12 meters per second, and you're not accelerating, you're going to continue at 12.5 meters per second. That's that shadow that I was talking about along the ground, okay? If you were to actually watch the shadow as the ball goes up and down, but you watch the shadow moving along the ground, the shadow neither speeds up nor slows down. It just moves along at 12.5 meters per second, okay? All right, so now the y component, that's a little different, the story there. And what's happening there is the y, if you were to do like a projection, I know the sun doesn't shine sideways, but just pretend that it does, and then you get a projection, a shadow along the y-axis, and it goes up, stops, and comes down. When it reaches its maximum height, it stops. And when it stops, that's when Vy is 0, and so you get that Vy is equal to 0, okay? So that's your, those two together give you your final velocity, okay, at the maximum height, all right? The acceleration, due to gravity, only a y component, is ay is equal to minus 9.8, but we're approximating it as negative 10 meters per second squared. And the time to get the maximum height is unknown. Okay, so a lot of work. I went through that in detail. When you get good at this, you could probably do this in like 2 or 3 minutes. But it's definitely worth doing it because now you're not going to make any mistakes when you go to substitute into those equations. Okay, so yeah, this is a lot of investment, but it's an important investment up front. Okay, now you're going to substitute into the four equations. Or choose which ones to substitute into. Okay, so let me cut and paste them in here like this. Whoa, wrong stuff. I don't know what just happened there. Copy, paste. There we go. All right. So here are the four equations. These should be in your notes, but let's go through them. Y is equal to 1 half AYT squared plus V naught YT plus Y naught. Okay, Y is your height. This is your height at a later time t. That's equation number one. Equation number two is Vy. It's your velocity at a later time t. Okay. Equation number three is just equation number one and two with time eliminated. So equation number three is good if you want information about height or y information, but you don't have time. Okay. And equation number four is the only equation about horizontal motion. Okay. It's like how far did you move horizontally given how much time. All right. So there it is. Those are the four equations. And now go back and see, what did I ask for? I said how long until it reaches maximum height? The question how long is time. Okay, so out of these equations, you want something that has to do with time and it has to do with height. Height is y, so that excludes equation number four. And then there's time. Okay, and so that means you're either going to be using equation number two or equation number one. Okay, and the equation which makes the most sense, because you don't know y, you don't know the maximum height. In fact, that's question B below. It's obvious that you have to use equation number two. Okay, so equation number two is the one you use. You know Vy, when it gets to maximum height, it stops, so Vy is 0. You know the acceleration due to gravity, Ay, negative 10. Time, that's what you're solving for. And the initial velocity, oh, it's initial velocity in the y direction. Whoops, like that. I forgot a little V naught y right there. Okay, so there's V naught y. Should put that in my copy paste thing here. All right, there we go. So Vy is equal to AYT plus V naught y. All right, so we're going to use equation number two. And it's really simple to solve. So this, I'm just going to, again, cut and paste. Copy, paste, I guess. So use equation number two to get the time. So you get Vy is equal to AYT plus V naught y. Just substitute in. Vy is 0, Ay is negative 10, t is the unknown that you're solving for, and V naught y is 21.7. Okay, so bring the negative 10t to the other side, divide both sides by 10, and you get that t is equal to 2.17 seconds. Okay, that's the time it takes to get the maximum height. All right, so let me pause for a second. And I don't see any questions in the chat. I'm just going to wait a second because I don't want to go too fast. And please, don't be afraid to just in the chat say slow down if I'm going too fast. I like to cut and paste because I tend not to make mistakes if I do that. But at the same time, I can see how I might go too fast if I did that. All right. I'm assuming that you're taking notes and you're also thinking about these things as I'm going along. All right. Okay, let me continue with part B. And part B is we're still looking at maximum when it reaches maximum height, but now I want you to actually calculate the maximum height achieved, okay? And so you're going to look at these equations here, and height is y, okay? Initial height is y naught, final height is y. So you want to calculate y. There's two equations that you could use. You could use either equation number one or you can use equation number three. Now that you have the time, you can use equation number one, okay? I chose to use equation number three in my solution. I don't know why. I mean, there's no real reason. I guess when I did it, I said, I'm just going to use equation number three. All right, so it is really straightforward, okay? So, use either equation one or three. And so I said, let's use three, all right? And this happens a lot when you solve these problems. At first, you don't have any choice. There's only one equation you can possibly use because there's too many unknowns. Okay. But then, once you get one thing, they start to unravel. Okay. So in equation number 3, you have the final velocity squared in terms of the other quantities. The final velocity is 0, so Vy here is 0. V naught y was 21.7. That was the y component of the initial velocity. Okay. 2, Ay was negative 10. Y is the unknown that we're solving for. Okay. And y naught is 0. Okay. I think it goes without saying. I mean, you just look for whatever equation has just one unknown in it, then you can solve it. Don't think that the unknown has to be isolated on the left-hand side or on one side of the equation. Okay, so like in equation number 1, y is isolated. Equation number 3, y is embedded, but it's still the only unknown. So it means you're going to have to rearrange. And maybe I went a little bit too fast in rearranging here. So let me just throw in another step in here. So that 21.7 squared, what is it? It's this number right here. Actually, let me round that off. And then negative, 2 times negative 10 is negative 20. Y minus 0 is just y, like that. Okay. And so that's what I'm solving for there. And then, just bring the negative 20y to the other side and divide through by 20, and you get that y is equal to 23.5 meters. Okay, so y is equal to 23.5 meters. And that tells you the maximum height. Remember, the hill is 20 meters high. And so, yeah, this definitely has a possibility of going above that 20 meters. If I'd made a mistake and, say, made the hill 30 meters high, it would not get to the top of the hill. If I did that, then later in the problem, when I go to ask you to calculate those things, you'd actually get a negative under the square root. Okay, so I mean, if that happens, then I made a big blunder. But I know what to look for. So let me put it this way: in 26 years of teaching this, I've never made that mistake. Okay, but you should know that, because I'm going to ask you to later on to redo these problems on your own, and I might even suggest that you might want to redo them with your own numbers. Okay, and when you redo them with your own numbers, you might accidentally create a situation which is physically impossible. And I'm just alerting you to the fact that when you do that, when you go to solve this quadratic, you won't get real answers. You'll get a negative number, the square root. Okay, so let me see if there's any questions. No, everyone looks good. All right, let's continue. Okay, so how long before it hits the top of the hill? So in this question here, we have to be really careful. All right, what's happened is I've made a little sleight of hand here. I've changed from the final position being the maximum height to the final position being the top of the hill. Okay, when that happens, you really have to redo the whole problem from scratch. Okay, and you can reuse some of the stuff that you used in the previous part, but you really do have to rethink it because something might have changed. And so what I'm going to do right now is switch back to my diagram and just repeat it, and I'll show you what changes when you talk about the final position being the top of the hill rather than the maximum height. Okay, so over here, if you take a look at our diagram, in the first part, we said parts A and B, we said, I want to know how long and how far or how high maximum height is. Okay, so how long until it gets the maximum height and how high maximum height is. Okay, and the final, which really doesn't mean final, it just, like, that's what everyone calls it, but so I'm going to keep calling it that, so to keep consistent with other textbooks and so on. But really, it's the I mean, because final, I mean, it goes past the maximum height, obviously, so that's not where it stops. Don't think of final as where it stops. It just means that point in the motion where we're interested after time t. Okay, and so that's there. But now we're interested in a final position of, let me do this in purple here. We're interested in a final position right there. Okay, at the top of the hill. So now you don't want to use this time here at all. We're talking now a time there, like that. And just like the time changes, all the other quantities might change too. So you have to rethink initial final position, initial final velocity, and all that. Okay, now in this case, the initial did not change at all. Okay, so my initial is still here. I'll do it in purple. It's still at the origin. So when I ask what's my initial position, these values are still legitimate. All right, but I had to rethink them because they might have changed. They might have changed, but they didn't in this case. Okay, so the initial position is still x naught is 0, y naught is 0. The final position, it was at the top here where the red dot is, but now it's where the purple dot is, and so these values are no longer correct. Okay, well, they were correct for the previous part, but they're not correct for this one. So we have to rethink them, and I'll do them over here. There's the final position has an X value, and the final position has a Y value like that. Okay, so let's think here. Do we know the X value? Well, that would be the projection down along here like this. And if you read the problem and so on, you don't. In fact, it's one of the questions that I asked you to solve. Okay, so let me get rid of those dashed lines. And there, that's question mark. Okay. In my previous class, I left all the construction lines behind. It became a real mess. So I'm going to remove some of the construction lines as I go along. Okay. So the X component of the final position, we do not know. We do not know. What about the Y component? So if I were to do a projection here, I start at my my ball there at the top of the hill, and I just project all the way over to the y-axis. What would I read there? Well, it's at the top of the hill, and the top of the hill is 20, so you would read 20 meters high there like that. Okay. Ta-da! So that's the new final. Okay. Final position. New final position. What about the new initial velocity? Well, these were the equations, and none of the values changed because nothing changed about the initial. I'm still at ground level. I'm just not interested in when it gets to maximum height. I'm now interested in when it gets to the top of the hill. Okay, so, and we'll look at those when we switch to the text editor. Okay, and then what about the final velocity, like Vx and Vy? Okay, well, again, we'll look at those when I switch over to the other one. But now Vy is definitely not 0. It was 0 when you were at the red dot, but now it's not 0 anymore. Okay, so these guys have also Vy is also changed. All right, and then what about the acceleration? Well, the acceleration has always been, you know, downwards here like that. It's just gravity straight down, you know, and you know, at negative 10 meters per second squared, and so on. Okay, so you'll notice I'm still using the same diagram, but I'm rethinking initial and final position, initial final velocities, because I did make that subtle change, and you know, this is a mistake that I've seen students make in the past. Okay, so let me see if there's any questions in the chat. Nope. All right, I'm going to switch over to the text editor here like that, and so let me just transcribe the values that I had. Okay, like this. So I'm cutting and pasting again, and there we go. All right, so these are the new values for part C here, because things, like I said, things have changed. Okay, and so the initial final velocity, initial position, X and Y component, they're the same because it starts at the origin. Okay, initial velocity, X and Y component, they're the same. Okay, we're still talking about the origin, so nothing changed there. What about the final position? Final position there, X and Y values, they're now different. Okay, X is unknown. All right, it was unknown before too, but it's still unknown here. But Y is known now. We know that the height at the top of the hill is 20 meters. So if you scroll up to when we did this before, you'll see that Y was unknown. Okay, but now Y is known. All right, in this second case. So there's an example of something that changed. It seems small, but it's not at all trivial, because we're going to need that Y is equal to 20. Okay, if you had left it at Y equals question mark, you know, the problem would get all messed up. All right, so now the new final position is X is unknown, but Y is equal to 20. Okay, what about the new final velocity? It's this. All right, so Vx is still equal to V naught x. That didn't change because, to explain it again, the velocity in the x direction the x component of the velocity doesn't speed up or slow down. There's no acceleration in the x direction. So if it starts off, if that x projection, that shadow, starts off at 12.5 meters per second, it continues at 12.5 meters per second. The y component in the previous problem was 0 because that's when it reached maximum height. But now it's past maximum height. It's on the way down. So whatever Vy is, we don't know its value, but it has to be negative because it's coming down. Okay, so there it is. There's Vy. And of course, the acceleration due to gravity didn't change. And the time is unknown. And this is actually a very subtle point too. We say, well, the time was unknown before, like this, and the time is unknown now. Yeah, but it's a different unknown time. So when you solved that time to maximum height, 2.17 seconds, don't use that number for part C, because it's a different time for when it gets to the top of the hill, because it's 2.17 seconds to get the maximum height, but then it's beyond the 2.17 seconds when it's coming down and then it hits. Okay, so just be careful about recycling values. Like, your knowledge is a bit fragile, so you'll say, oh, I have time, I just solve for time, so I'm just gonna use that from here to there. But no, it's a different time. Use here, this is the time until you get to maximum height, and this unknown time here, which we're going to solve for, is the time until you get to the top of the hill, which is a different time. Okay, so be careful about those kinds of subtleties. All right, let's see, any questions? No, you're looking good. Okay, I assume. Maybe everyone's fallen asleep at the keyboard. All right, I'm just kidding. Okay, so now what? Now, I won't rewrite those four equations, but you're going to relook at those four equations. Okay, and you're going to say, well, which one do I want to use? And I'm just going to cut and paste a really long answer here, but we'll go through it slowly. Okay. The question was, so a lot of work there, you might have lost track of the question. The question was how long before it lands on the top of the hill. So we're solving for time here. Okay, so solve for this. Okay, and if you go through them, through the equations there, you'll discover that the one you have to use is number one. Okay, you can't do it with any of the other ones. Number one is the one you want to try to avoid the most, because that's the one that's going to get you to a quadratic. But if it's unavoidable, you have to go that way. Equation number one is y is equal to 1/2 ayt squared plus v naught yt plus y naught. Okay, so substituting in y, that's your final height. That's 20 meters. It's 20 meters above the ground. 1/2 ay is -10, the acceleration due to gravity, t squared. V naught y, that was the y component of the initial velocity, we found to be 21.7. Okay, times t. And then y naught was the initial height, which was ground level 0. All right, so there's the substitution. There's the substitution into that equation. Okay, now the rest of it is just rearranging and cleaning it up a bit. 1/2 of -10 is -5. There's that. Okay, so this part of it is just that part of it. The plus 0, of course, goes away. The 20 on the left-hand side, I subtract 20 from both sides. It becomes -20 on the right-hand side. And there it is. Now, why did I rearrange it that way? Because we're heading towards the quadratic. All right. And so I've always done this since, I don't know, since my high school days. I always like just dividing by the coefficient capital A. I just like getting it out of the way. This way A is 1. So you see that -5 there? I'm just going to divide through by -5. -5 divided by -5, 1. Positive 21.7. So you got to include the sign there. Positive 21.7 divided by -5 is a -4.34. And then -20 divided by -5 is +4. Okay. And then identify that A is 1 by construction, B is a -4.34, and C is 4. And there's the quadratic formula, like that, to solve for it. T is equal to -b plus or minus the square root of b squared minus 4ac divided by 2a. This is where, that's the square root where if you made your hill too high, like this, if you made your hill too high, C would be too big. And if C is too big, you get a negative in the square root. Okay, so that's where things could go bad in this problem. Okay, but again, like I said, that isn't going to happen right now. Okay, and then substituting in the numbers. Okay, and you just have to be careful, like that -4.34. When you square, you're squaring everything, including the negative. And of course, when you square a negative, you get the positive. Okay, don't make the mistake of not squaring the negative as part of it. Otherwise, you'll get a negative under the square root, and it won't work. Okay, so there it is. And working it through, you get 2 times, you get 3.10 seconds. Let me put seconds in there, and 3.11 seconds. And you go, which one? Well, I guess question mark. Well, before we answer that, let me just show you another way to solve the quadratic. I wouldn't call it cheating exactly. I mean, you guys have probably solved quadratics enough in your lifetime. You can use this web page here. Okay, here's a nice little web page that you can solve quadratics. The tests are open book. A lot of programmable calculators will have little programs to solve quadratics for them. Feel free to use any one of them, or just do it manually, whichever you like, or two ways, and then check. But basically, math.com is a really nice site. It's a site that has a lot of these kinds of, like, I would say, high school level math type equations, which are always good to have at hand. And I mean, this is a long URL to memorize. I don't expect you to memorize that. You could just Google for solve quadratic equation online, and you'll get this site and a bunch of other sites come up too. Okay, and there you could just type in A, B, and C, the coefficients A, B, and C. You hit the solve button, and you'll get the two equations. Okay, we get two positive equations, and you go, well, which one? There's two positive solutions. You go, well, which one do you want? Usually, when one is negative, you go, oh, I'll just choose the positive one. Makes sense. Okay, but no, we gotta be careful here. Okay, we gotta interpret which one we want. And you say, well, which one do we want? And how do I figure that out? And you have to look at the diagram. Okay, so let's switch back to the diagram here. And it is getting a little messy, but I think I can still get this last bit out here. Let me draw the 20-meter height level. Okay, and I'm going to draw it in red here like this. Maybe not. Let me draw it in green. I know I'm making a mess of the diagram, but this is the last we're going to need of this diagram. So there, you see that green line there? That green line is the 20-meter height. Okay. The black line that you're seeing, that you see there, the one of the original black line, that was the original trajectory. And you ask yourself the question, at what time is this thing at 20 meters height? Because that's what that first equation, when you set y is equal to 20 meters, that's what you said. You said this thing is how long until it gets to 20 meters? And you know what? It gets to 20 meters twice. It gets to 20 meters here, and then goes above 20 meters, and then gets back to 20 meters there. And so it's at the 20-meter mark twice. Well, guess what? This is the 3.01 seconds, and this one is the 1.33 second mark. Okay? And so it passes the 20-meter mark the first time on the way up at 1.33 seconds, and it passes it again on the way down at 3.10 seconds. Okay, and by the way, this up here was maximum height was 2.17 seconds, like that. Okay, so you take a look at these and you go, which one do you want? And the answer is obviously you want the larger of the two. That won't always be the case. I mean, I could rearrange the problem so that you actually want the 1.33 seconds, but it's not that bad. Just go back to the diagram, think about what those two times mean. Again, they are the time at which this ball passes the 20-meter mark, and it's going to pass the 20-meter mark twice, once on the way up and once on the way down. And when you do that, you pick the time that you want. Do you want the time on the way up or the time on the way down? And it's pretty obvious you want the time on the way down here. So it's the 3-second mark. Okay, so let me just show you one more thing before I switch back, so I don't have to keep switching back. See that 2.17 seconds, that maximum height? Guess what? That 2.17 seconds is exactly in the middle of the 3.01 seconds and the 1.33 seconds. In other words, the time it takes for the ball to go from the on the way up from the 20-meter mark to maximum height. I'm drawing it in here in purple, so I'm filling it in purple there like that. Hopefully this doesn't get super messy. All right, let me know if this is too messy for you guys, but that part there, the time it takes for that, it actually turns out to be, let me just look at the number, it actually turns out to be 0.84 seconds. The time it takes to go from the 20-meter mark to maximum height on the way up is 0.84 seconds, and guess what? The time it takes to go from maximum height back down to the 20-meter mark on the way down is 0.84 seconds. So the maximum height is exactly in the middle of the parabola on the way up and on the way down. Okay, so let's go back and finally finish this problem off. And here's the rest of the solution, like that. Okay. So, you don't have to go into a long explanation here and just like see the diagram for why you want t equals 3.01 seconds, okay? And then I say, by the way, the maximum height obtained at t equals 1.27 seconds is right in the middle. Notice that the 3 second is the 2.17 plus 0.84, and 1.33 is 2.17 minus 0.84. Okay, and you wonder, how did I get that 0.84? Well, I just looked at the difference between those two numbers and 2.17. Okay, but the point is that the maximum height is in the middle of those two little branches of the parabola. Okay, because the parabola is totally symmetrical around maximum height. All right, any questions with that? Let me take a look here. I know you're lagging, but there you go. All right. Or you're not lagging, but there's a 30-second lag. Okay. So the last two questions here are pretty straightforward. How far did it travel horizontally before landing? Okay. So for this, whenever you're talking horizontal, you take a look at those four equations. There's only one that has horizontal information. That's equation number 4. And so, I mean, it's so trivial. I'm just going to cut and paste the entire solution there. I mean, usually once you solve that quadratic, everything unravels after that. It's quite straightforward. So substitute in number 4 to find x. X is like the horizontal distance. It's the x component of the position after the at the end of the motion. Okay, and so x is equal to v naught xt plus x naught. And so that just gives you, plugging in the numbers, v naught x was 12.5. T, we're going to use the time for the full until it actually lands on the top of the hill, which is 3.01 seconds. And the initial horizontal position was 0 meters. Okay, and so it turns out to be 37.6 meters. Okay, that was easy enough. And then finally, the next one, also pretty easy, but a little bit of a subtlety, because I'm asking for polar information, and look at how I asked for it. It's like, what is the velocity just before it hits the top of the hill? And answer with just the magnitude. So whenever you're talking Cartesian, you're talking x and y components. Okay, it's like the vector has been broken up into its two pieces. Okay, it's x and y piece. But here, whenever you talk magnitude and direction, you're talking polar. So answer with magnitude, it's like saying answer polar. Now polar also has the angle, but I didn't ask for the angle. I just said, just give me the magnitude. All right. All right. So what are you going to have to do? You're going to have to get, because everything in the equations is Cartesian. You're going to have to get the Cartesian answer first, and then convert to polar. Okay. Now, final velocity, what is that? That's going to be Vx and Vy. Okay, Vx and Vy. And by the way, I also said just before it hits the top of the hill, so just before it hits. That's important, and we went through this when we looked at 1D, but it's still important here. Those equations know nothing about the ground or colliding with things. So, a typical error that's made, you say, well, when it lands, it's going to have 0 velocity because it stops. But no, the equations don't know about that, and you shouldn't think about it that way. You should think about it as just before it interacts with the ground. As soon as that ball interacts with the ground, those equations no longer apply, because you don't have acceleration just due to gravity. You have acceleration due to gravity and the interaction with the ground and whatever else might be happening, which is why the ball bounces. Okay, and that motion is very complicated, and there's nothing in those equations that say anything about bouncing or anything like that. Okay, so don't think about when it hits or when it lands as actually after it lands, or even during the landing. Just think of it as just before. And I think you would agree that before it interacts with the ground, it's moving downwards with some velocity. Okay, and so you're going to need Vx and Vy, the two components. All right, Vx we already know. All right, cutting and pasting these. All right, Vx we already know. All right, why? Well, because Vx is the same as V naught x. We went through that. There's no change in the x component of the velocity. Okay, and we already know that that's going to be Vx is V naught x is 12.5 meters per second. All right, we need Vy, which is the y component of that, so that we can finally solve for the magnitude. Okay, and Vy, you say, well, which equation can I use? And you could use either, I think, 2 or 3 here. I use 3 on purpose because I want to show you that you actually get 2 solutions there. Okay, and so there was a reason here to choose that, but I mean, you could choose whichever. There's equation number 3, all right, and we want Vy, and so we know V naught Y, we know AY, we know Y, and we know Y naught, and so I just substituted those numbers in. V naught Y was 21.7, AY was -10, Y minus Y naught, well, Y naught is 0, Y was 20, so that's 20, and working that through, you get that you just work it through on your calculator, you get that Vy squared is 70.89. Okay, now at this point you would just take the square root and you would get 8.42, but be very careful. The calculator only gives you the positive solution. There's 2. So let me just take a little bit of an aside here. Suppose I said to you z squared is equal to 4. What's z equal to? Like that. What are the 2 possible values of z? And if you just did this in your calculator, you just did the square root of 4, you would get 2. And that is right, but that's incomplete because you know what? It could also be -2. Okay, so even z squared is equal to 4 is a quadratic because there's a squaring in it, right? And you know that 2 times 2 is equal to 4, but also -2 times -2 is +4 because multiplying 2 negatives together gives you a positive. And so -2 all squared, that is -2 times -2, is also 4. So the calculator doesn't give you the -2 part, it just gives you the +2, and it expects you to know that there's 2 solutions there. Okay, and so when you take the square root, so that was just for an example, but when you take the square root of the 70.89, you're going to get 8.42, but you have both a positive and a negative. And you might say, well, what does that positive and negative mean, and which one do I want? Well, think about it. It passes the 20-meter mark twice, once on the way up, that's your positive root, and once on the way down, it's the negative root. So choose the negative solution because it's on the way down, okay? So, like you got to be careful about these things because you might just miss that. You might not be thinking about that, and then you miss that point completely. And then, depending on the context of the problem, it just goes bad after that, okay? So remember that whenever you have a quadratic, even a quadratic as simple as, Vy squared is equal to a number, that there's 2 solutions. There's the positive and the negative solution, and you want to make sure that you pick the right one. Okay, there we go, we chose it. At this point we have this. We know that Vx is 12.5 meters per second squared and Vy is -8.42 meters per second. And if all I wanted were the Cartesian components, that would be it. But we want the magnitude. And the magnitude is like the r in polar coordinates. So in polar coordinates, when we did the work on vectors, I called r the magnitude and theta the direction, okay? And it was abstract. I didn't tell you what we were talking about with r. I kind of implied it was position, okay, like a radial direction or something like that. But I mean, vectors work for velocities too, in which case what you're talking about there with the magnitude is just how fast you're going, irrespective of the direction. So when I say I want the magnitude of the velocity, basically what I'm asking for is the r value, the equivalent of the r value. And how do you get that out of x and y? Well, the magnitude is obtained from x and y using the Pythagorean theorem. Okay, and the reason, you have to go back to the vector video where I show you, the right angle triangle that's formed. But basically, the magnitude v, and so this is just how fast you're going, irrespective of the direction. Okay, no x, no y, no direction, just how fast are you going when you hit the ground. Okay, it's going to equal the square root of the x component squared plus the y component squared. Okay, the x component was 12.5, square that. The y component was -8.42, but square the whole thing, including the negative sign, in which case the negative goes away. Okay, and you get 2 positive numbers there. Take the square root of that, and it turned out to be 15.1 meters per second. Okay, so that's how fast it's going before it hits the ground. Now, just to give you an example of the kind of mistake that would have happened if you had confused the signs there. Okay, I didn't ask for the direction in this problem, but if you did it, notice that the x is positive, the y is negative. That angle's in the 4th quadrant, and as you'd expect, because it's coming down. Okay, remember, if the x component is positive, the y component is negative, it's in the 4th quadrant, it's coming down. Okay, but what if you had accidentally chosen the positive solution here? Well, then you would have had the x component positive and the y component positive, in which case you're talking about 1st quadrant, and that's right, on the way up, but not on the way down. Okay, so yeah, it makes a difference. You got to think through that. Okay, there it is. That's the problem. Okay, right around roughly the 1 hour mark. Don't worry, the question number 4 will just take a second. We'll do that. So what I recommend you do later is repeat this entire problem. You know, hopefully you were taking notes, or you could rewatch the video and then repeat the entire problem on your own. You could use the same numbers. You could change the numbers. Okay, and you know, it's more important that you get the procedure right and do it without looking at, you know, how you did it. Just try to memorize the steps in solving this. Okay, so that when you get to the test, you know, you won't be stuttering over you know, any of the steps. You'll move through it fluently. And if you take a look at part B, question 2 and 3 here, I want you to do these. Okay, so they're variations on the previous problem. So variation number 2 is repeat that problem, but now assume that there is no hill. In other words, the ball leaves ground level, it goes up, and it comes down to ground level. Okay, so the final position is going to be at ground level, not on the top of a hill. Okay, and then part 3, or part 3, I mean practice problem 3 here is repeat it, but this time assume that you're at the top of a hill 20 meters high and you throw it up and it comes down. Okay, and it lands at ground level. All right, and there you go. Okay, and again, you can vary the numbers here. Just be aware that if you vary the numbers in part 1, in question number 1, and you don't make the hill, you make the hill too high, then you're going to get a problem. Okay, when you go to solve for the quadratic for time. In 2 and 3, that you won't have that problem. Okay, because you know, it doesn't matter how high the hill is, the ball will always make it to the ground level. Okay, so there you go. There's a couple of practice problems, and these are problems to just do on your own, in addition to the assignment problem that I'm going to be giving you for next week. Assignment problems that I'm going to give you for next week. Okay, and if you do 1, 2, and 3 here, you've pretty much done all the possibilities. I mean, 1, you're below where it lands, the other one you're above where it lands, and then the third one is you're at the same level. Okay, so you've gotten all 3 possibilities under or you've practiced all 3 possibilities, and you should be good then. Okay. All right, let's do number 4. It only takes a second. And all of these, to be honest, all of these uniform circular motion uh, problems are pretty simple. There's 3 quantities. There's the radius, that is the radius of the circle. So uniform circular motion, you're going around in a circle. Okay, and you're going at the same speed. You're not speeding up or slowing down, and your radius of the circle isn't changing. Okay, towards the end of the course, we're actually going to do a generalized rotational motion, in which case you could start off slow and speed up, or go fast and then slow down. Okay, and so that's later. Right now, that's the uniform. The circular is that you stay on a circle, and the uniform is that you don't speed up or slow down. Okay, so let's do it. I'm riding a bicycle around a corner with a radius of 7 meters. Okay, the fastest I can turn without slipping is about a quarter of the acceleration due to gravity. Okay, so if I go around the corner too fast, my centripetal acceleration will be more than a quarter of a g. And if that's the case, I'm in danger of slipping. So I want to stay at or below a quarter of a g. And the question is, how fast can I go around? Can I go around the turn safely? Okay, so how fast can I be going? So I'm asking, whenever you see how fast, that's basically I'm asking for the velocity. All right, so let's do that one. Okay, and let me just cut and paste the equations that are involved. Well, first the values that are involved, and then the equations. Actually, I'll just give the whole solution. Just cut and paste the whole thing. Go through it a step at a time. So you know, just you don't even need a diagram for these, to be quite honest. What did I tell you? I told you that the radius of the turn was 7 meters. Okay, it can't be tricky there. I mean, the worst I could do is maybe give you a diameter instead of a radius, and just remember that the diameter is twice the radius. Okay, but okay, I gave you a radius, 7 meters. The acceleration I told you was a quarter of g, and so that's 0.25 times 10, or 9.8, but round off to 10. Okay, so that's 2.5 meters per second squared. If I accelerated more than that, I'm in danger of slipping. Okay, and the 3 equations are v is equal to 2 pi r over capital T. So r is that radius, v is the velocity, pi is pi, of course. And t, capital T, is what's called the period. It's the time to go around the circle once. Okay. Now, even if you don't make a full circle, you're making a partial circle, like you might imagine if you're going around a corner. these equations still apply, but if you were to extend it to the full circle, then the time it takes for that full circle, that would be the period. Okay, that would be the period. No information about that. I didn't say anything about times in this problem. Okay, and so equation number 1 is out. Okay, equation number 2 is the same as 1, but now in terms, it gives you acceleration rather than velocity. So the acceleration, centripetal acceleration, is 4 pi squared r over t squared. Okay, and then finally, if you eliminate the period from 1 and 2, you get equation number 3, which is a is equal to v squared r over t. So v squared over r. Okay, so a is equal to v squared over r. Okay, that's obviously the one that you want. Okay, now you're not solving for a, so just because a is isolated here, that doesn't matter. V is the only unknown, so that's what you're solving for. So just rearrange it in terms of v, isolate v. Okay, so multiply both sides by r, like that, and then take the square root of both sides, and then you get v is equal to a over r. V is equal to the square root of a over r, like that. A is a quarter of g, which is 2.5 meters per second squared. R was 7, okay, and you multiply them and take the square root, and you get 4.18 meters per second. Okay, that's how fast I could be riding on my bike when I go into this turn, and expect that my acceleration, my centripetal acceleration, will be a quarter g, which is the limit of my of what I can do safely. Okay, if I were going faster, then a wouldn't be higher, and there's the danger of slipping. Okay, and I try to make my numbers realistic. I mean, 7 meters is about 20 feet, 21 feet. Okay, and that's about right for a turn. You usually make on a bicycle, and that turns out to be about 15 meters. 15 kilometers per hour. Or if you converted it to miles per hour, because maybe your intuition is better in miles per hour, that would be about 10 miles per hour, and that's roughly right. I mean, you could probably do it faster than that, but roughly speaking, 10 miles per hour for a turn on a bike is about right. Okay, safely. All right, that's it. Let me see if there's any questions in the chat here, and let me just ask: are there any other questions? I'll wait a bit because of the 30-second delay, and I'll also type in here. That's it. That's all. Any questions? If not, we'll end the stream. Okay. So let me know if there are any questions. Give me some feedback that you're all okay, and if that's the case, then I'll just end the stream. Did I put everyone to sleep at the keyboard? All good. No questions. Great. Okay, well, if you do think of questions later, there's always the Google Hangout in the evening. Try not to wait till the last minutes to do assignments, because it's awful when people want to catch me on the Friday when it's due, and like about 8 o'clock, 8:30, I'm heading off to bed, or kind of winding down for the night, and I may not see the email till the next morning, and so that's not a good idea. All right, bye bye.